Hello friends, today we are going to discuss one of the important molecular technique in genetic engineering, isolation and purification of nucleic acids. Isolation and purification of nucleic acids. You know, almost all gene manipulation experiments require pure form of DNA or RNA or even both for successful completion of genetic experiment. Therefore, techniques, that means isolation and purification techniques, plays a vital role, that means an indispensable role for the successful completion of gene manipulation experiments. Broadly, there are three steps pertaining to the isolation and purification technique. Say what we call BSR. Number one, B means breakage of the cell to expose the nucleic acids. Number two, separation of nucleic acids from the rest of the cellular components. Number three, recovery of nucleic acids in pure form. Simply called BSR. BSR. Broadly, technique, breakage of cell to expose nucleic acids. Number two, separation of nucleic acids from rest of the components. Four, recovery in pure form. There are two different ways, that means for purification of DNA, purification of DNA and purification of RNA. Here we are going to discuss about mRNA. It is most commonly used. The thing is, in both the techniques, there is the process, the common step is cell lysis and have a different protocol. For DNA, there are two ways for purification. We'll discuss them by one. So it's about the brief outlook of isolation and purification techniques for nucleic acids. There are broadly DNA and RNA. For RNA, generally we're going to discuss about mRNA. For DNA and both RNA, the common thing is cell lysis. That means I told you already, the first step of purification techniques to break the cell and expose the relevant nucleic acids. Here the cell again of three kinds. It is of bacterial cell or plant cell or animal cell. For example, if it is bacterial cell, the first, that means combination of enzymatic and chemical reaction, say through enzyme lysozyme and the chemical EDTA, ethylene diamine tetraacetate, then followed by the detergent sodium dodecyl sulfate. Whereas in case of animal cell, then most of the animal cells they break it out, that means lyse it out by means of a simple detergent SDS, sodium dodecyl sulfate. But plant cells is a bit different because they are strong cells because of having strong cell wall. So to break the same required a special technique. Say they have to get frozen off, then with the help of mortar and pestle they have to break down. So it is generally convenient method for plant cell lysis. Okay, we will discuss one by one. As I told you, the cell lysis is a common step for both DNA and RNA purification. The cell lysis, the cell lysis. These are three kinds. For bacterial cell, there is one different kind. Animal cell, then the plant cell. For bacterial cell, it's a combination of enzymatic, that means lysozyme, and chemical, that means EDTA, ethylene diamine tetraacetate, followed by SDS, sodium dodecyl sulfate, which is a detergent. Sodium dodecyl sulfate. Whereas for animal cell, we use most of the animal cells, even particularly the cultured animal cells, they break down by means of SDS, sodium dodecyl sulfate. Whereas for plant cell, it is mortar and pestle. Because of strong cell wall, they require extra effort. That means a rough, it was what we call harsh technique generally opted for plant cell wall because of its strong cell wall nature. Because whereas the rest of the cells are like animal cell and bacterial cell, this is an usual process. For bacterial cell, both enzyme and chemical will be added. Okay, it's about the cell lysis. That is the first step in purification. That means who has to expose the contents of the cell. Say they have to break down now. So this is common for both DNA and RNA as well. But first we'll discuss about purification techniques of DNA. You know, purification of DNA. First we'll discuss, then we'll draw a chart for better understanding. For example, we want a purified DNA. After the cell lysis, you know, it will contain a degraded form, what we call cell debris. They have to get separated. So first you have to centrifuge the degraded form so that we can get a pellet of debris at the bottom. And the supernatant, this is very important, it had to be separated out. And the supernatant should be subjected to a phenol, so that proteins can get precipitated at the interface of an aqueous and the organic phase. The aqueous phase contains dissolved nucleic acids. This has to be separated. This aqueous phase has to be separated to RNAs because we want only DNA, so that the RNA shall get degraded. Then the DNA, they shall be isolated. Say for example, the first precipitation by ethanol followed by centrifugation. That means isolation by centrifugation, then suspension in appropriate buffer solution. That means here it's a sequential step. I told you it is what we call separation. That means purification of DNA is like, you know, not directly but purification by removing unwanted cells, cellular components. First you separate the cellular debris. Number 2, separate the protein. Number 3, separate the RNA. Number 4, then the DNA in recovery form. That means in the pure form of DNA we can get recovered. This is called purification of DNA from cellular components. It's not a direct purification, it's like indirect, and it's a time taken and laborious process relatively when compared to the direct techniques. Say how it ends. For example, after the cell lysis, that means cell extract, you will get cell extract. It has to be subjected to centrifugation. The most important point is at low speed. Very important. Then you will get debris. You will get debris in the form of pellets at bottom. Debris pellets at bottom. Then the supernatant. The supernatant subjected to phenol for protein precipitation. For protein precipitation between aqueous and organic phase. You know, this is aqueous phase, and this aqueous phase has to get separated because it contains soluble nucleic acids. Soluble nucleic acids, and this has to be subjected to RNAs because we have to remove RNA from it. Degradation. And finally the DNA. How? It has to be precipitated by ethanol. Ethanol precipitation followed by centrifugation. Then finally suspension in appropriate buffer. So this is a schematic representation of how the DNA is purified. That means the one way, what we call from cellular components. This is type 1. First, the cell extract, which we get after the lysis. Then the subject the same to centrifugation, but at low speed, so that the debris can be accumulated in the form of pellet in the bottom. Then the supernatant, which we get, then subject the same to phenol because it precipitates the protein at the interface of aqueous and the organic phase. Then we want aqueous phase. This is very important. We want aqueous phase. And subject because it contains soluble, that means nucleic acids in soluble form. Then subject the same to RNAs because we want DNA only now. Break down the RNA. Then the DNA, the subject the same to precipitation with the help of ethanol, followed by the centrifugation, then suspension and appropriate buffer. It's a brief procedure for isolation and purification of DNA. That means first we have removed the unwanted debris for number 1. Number 2, we have removed the proteins. Number 3, we have removed the RNA. Then finally the DNA. It's called phase method. It's a time-taking process. Okay, let us see how the direct purification technique works. Okay, in direct purification, the name it implied selective separation. It's relatively best when compared to the indirect method. In direct purification technique, we selectively remove the DNA from the rest of the compounds. There are two broad ways. Say direct purification of DNA. There are one, what we call cetyl trimethyl ammonium, CTAB. Another one is guanidinium thiocyanate. This is very important. This is actually denaturing agent. Direct purification DNA broadly involved, and it's again of two types. Here the thing is that there are two chemicals which are majorly responsible for this technique. First one is cetyl trimethyl ammonium. What exactly it do? Say the cetyl trimethyl ammonium, it combines with nucleic acids to form an insoluble complex. Then it will be subjected to precipitation. Then it will be subjected to high salt buffer solution, because this high salt buffer solution will release nucleic acids, and it will be subjected to RNAs, to remove RNA. Then DNA from a precipitation by ethanol. It's just one of the important direct way to purify DNA, because here the thing is, this particular chemical cetyl trimethyl ammonium, CTAP, it forms insoluble complexes with nucleic acids. First, that is point number 1. And after forming insoluble complexes, they shall be subjected to precipitation through ethanol. Then subjected to high salt solution, because this high salt solution will release the nucleic acids. Okay, high salt solution. After releasing the nucleic acid, they are subject to RNAs, because we want only DNA in pure form. That means the purified DNA will be isolated by means of precipitation in ethanol. The pure DNA recovery, what we call. This is a brief procedure for how the direct technique through cetyl trimethyl ammonium works. Then another way, what we call guanidinium thiocyanate, and how it works. It's actually a denaturing agent. There are two ways again here. Here are two ways. In the first way is very simple. Silica particles. This is very important. Silica particles plus DNA. They form strong bond. They hold tight together. That's like complementarity, but just for analogicity, for comparison, I'm saying they hold tight together. Under the presence of a denaturing agent, what we call guanidinium thiocyanate. Then recovery by centrifugation. After this centrifugation, the simple step, recovery of pure DNA. recovery of pure DNA. One more way, what we call column chromatography technique, simply called column chromatography. That means we knew that is a basic pad technique, In column, we have column chromatography, we have to add silica. Say the silica we have to add. The silica. This is, for example, silica. Then you add the cell extract and also the guanidinium thiocyanate, simply represented as GT. Later, what happens, the silica, they bound to the DNA, and the rest will go away. That means the recovery will be done later onwards, just like the usual procedure, The recovery will be later. The first, the most important point is binding of DNA with silica through column chromatography. This is very important. Under the presence of denaturing agent, guanidinium thiocyanate. So these are the two ways. Through the denaturing agent guanidinium thiocyanate, we can directly purify the DNA. In fact, the first way, this CTBA, cetyl trimethyl ammonium. Then you have to form an insoluble complex. Then precipitation. Then you suspend the same in high buffer solution and high salt solution. Then the nucleic acid will come out. That means removal of nucleic acids. Then you add RNAs to degrade the RNA. Then you purify the DNA. That means recovery of DNA through suspension with the help of the ethanol. It's a usual process. So it's about two techniques for purification of DNA. Then regarding purification of RNA, we are going to discuss about mRNA here because this is very most commonly used. mRNA purification is a bit different. Purification of mRNA here. The first phase in purification, what we call cell lysis, is usually is the same in case of purification of DNA. If it is a bacterial cell, subject the same to the enzyme lysozyme, then the chemical EDTA, that means thin diamine tetraacetate, then followed by the SDS, what we call detergent, sodium dodecyl sulfate. Then if it is animal cell, that means particularly the culture's animal cell, you add SDS, sodium dodecyl sulfate. Then if it is plant cell, then just because of strong cell wall, you have to mortar and pestle. And after that you will get cell extract. So it is common for both DNA and RNA purification. And what will you do? First, after you get a cell extract, say this is cell extract, subject the same to phenol or chloroform mixture. But this is called for deproteinization. After that, you subject the same to centrifugation. You will get the upper aqueous phase. Subject the same to precipitation by ethanol or isopropanol. Precipitation. That means the cell extract, then the next phase is deproteinization. You add phenol that means a phenol chloroform mixture. Will remove the protein, then subject the same to centrifugation. You will get the upper aqueous phase which contains the nucleic acids. Then the same to precipitation with the help of either ethanol or isopropanol. This is very important. And you got the nucleic acid solution. Then here this is very important. After you get the nucleic acid solution, how we have to remove? This is called oligo DT, cellulose. In the sense, say, how to look? This is cellulose bead. Oligo DT means 80 dinucleotide in if you chain, oligo chain, This is called cellulose bead, and this is DT. Say this is eukaryotic mRNA. There is a polyadenine tail. Say this is mRNA, for example. This is mRNA, and at the 3' end there is polyadenine tail, what we call simply poly-A tail, and this poly-A tail is attached to this oligodendrocellulose. It's just like, for example, you hold the tail of a dog, or you hold, or else you, just for comparison, for better understanding, I'm saying, just like we hold the tail of a dog or some other animal, this same the poly A tail. Say this is poly A tail, and I'm oligodendrocellulose. It will hold like this. Because of this, the rest of the nucleic acid means which are present in the aqueous phase, say DNA, say RNA, say tRNA, will get eluted. Okay, I will tell you how it get eluted. Okay, but first we have to particularly identify that chemical, that means the compound which bounds, which attaches to the mRNA and which aids in the successful recovery of pure mRNA. This is very important, and this is called oligodendrocellulose. You know, because of this attaches, this bonds to poly A tail of eukaryotic mRNA. Then the rest will take place. And how? This through affinity chromatography. The same, but better presentation I will track here. And after this we get it, the pure form of mRNA. Okay. This is a column chromatography, no? Then it contains oligodendrocellulose. Is able to magnify the same. If we magnify the same, this will be this here. That means cellulose bead and the AT tail. Then this mRNA. That means poly A tail of this is mRNA. You know. This, so the first step is done. The oligodendrocellulose, the cellulose binds with the tail of, that means hold the tail of, that means poly A tail of mRNA. Then followed by the next important phase, you run the chromatography by high salt solution. High salt. Just run the chromatography by high salt. Because of this elution, that means elution of DNA, tRNA and rRNA. That means DNA will be removed, tRNA will be removed, RNA will be removed, and we want our desired compound, that means mRNA, which has been targeted by the oligodendrocellulose. Then you add the low, this is step 1 and this is step 2. Then you add low salt solution. You add low salt solution. Low salt. Then followed by, that is usual procedure, ethanol precipitation. This is ethanol supernatant. This is ethanol supernatant. And mRNA in the form of precipitate. For example, this is B. This is mRNA. Followed by the centrifugation. This is how the issue ends. With respect to mRNA, it's a bit different. The most important compound responsible for the successful purification of mRNA is oligodendrocellulose, because this kind of oligodendrocellulose means dinucleotide. The AT in oligostrand. That's it. They will bind the mRNA. That means the poly A tail. Where this is very important. The poly A tail, which is present at the 3' end of the eukaryotic mRNA, will be held tight by this. Then the rest, with the help of high salt solution, you separate the DNA, you separate the tRNA, you separate the RNA. Then you have, with the help of low salt solution, you separate, you will get this complex. Then through ethanol precipitation, that means you will get the mRNA, then followed by centrifugation. This is how, that means precipitation with ethanol, isolation, then suspension, appropriate buffer, the most common ending steps. But here the chemical, this is very important. In case of DNA, that means direct method, cetyl trimethyl ammonium, CTAB, then guanidinium thiocyanate, other way, for direct purification of DNA. And here the oligodendrocellulose, that means identifying the chemical responsible for the successful purification of the concerned nucleic acid is very important in this particular technique, so that we will get the desired product, say whether it is DNA or even mRNA. It's because it all had a huge bearing on the successful completion of gene manipulation experiment. Okay, so today for today's class, this is about isolation and purification technique for nucleic acid. In next class, we'll discuss some of the topic.